We have Divita Gupta with us, who is going to introduce us to the exciting world of astrochemistry. A little bit about Divita Di. She did her master's in 2018 from IISER-Mohali under the guidance of Professor S Viswanathan. Then she moved to the Institute of Physics in Rennes, France, where she is doing her Ph.D. with Professor Ian Sims. Her work mainly involves examining the products of low temperature chemical reactions, which are important in the cold astronomical environments. So, without further ado, let's get started with the talk.
Thanks, Devang. Let me start my screen sharing. Is it good for everyone? You can all hear me and see my screen?
Yes, it's perfect.
Oh, awesome. Okay. Good evening, everyone. So first of all, I'm really excited when Devang contacted me that many students are interested in astrochemistry, because I myself got to know about this field when I was in my second year, I think, because I did my first year master's summer project with Professor Bagla. And then he was the one who told me there is this field called astrochemistry, and what I was interested in and what I was talking about was not astrophysics and actually astrochemistry. So I'm really excited to share some of the things I know from this field, and happy to talk to you about more as well afterwards. So the first thing I will talk about is the first part. So the talk has basically two parts. The first, I will introduce the field of astrochemistry and how it differs from the field of astrophysics, which is quite known to everybody. And then I will also talk about my work, and interestingly, how the field of rocket science was key to proving Arrhenius partially wrong. Okay. So I will also, within the astrochemistry discussion, I will talk about the different types of chemistry that exist. There's ice phase chemistry, there's gas phase, and there's also chemistry which happen at these interfaces between dust rain and ice phases, and even the ice and gas phases. And then I will talk about some of my work, which has been involving gas phase reactions with CN radical and methanol and a few aromatics. And then I will end about on future outlook and some perspectives. Okay, so what is astrophysics? I think you all have some introductory courses in astrophysics, but I think it's quite well known. Astrophysics revolves around the physical laws of nature. What it concerns stars and other big celestial bodies, how they are forming, what their properties are, and how they interact with other celestial bodies. In contrast, astrochemistry is the chemical interactions that occur in space. So there are these celestial bodies in space, but within them, what are the difficult chemicals and the different chemical interactions? That is what is covered under astrochemistry. So you have how these chemical interacts, how the chemicals interact in the gravity-less environment. That's very different from when we are studying molecules in our terrestrial environments, where we have space, where we have different densities and completely different conditions. And also the major key within the chemical components, the key distinction is astrophysics will always involve, even if you're talking about the chemical species, you would have more really light atoms. You would have hydrogen, you would have helium, and maybe you would come to carbon monoxide, but you will never go beyond that. And you would also have maybe really heavy metals, but that's about it. Whereas in astrochemistry, you actually start seeing species which you are used to in your chemistry courses maybe, and actually even beyond that. There are some species which were not known to be present on Earth, but were first seen in astrochemical environments, and then you realize that, oh, we could actually form these species. And that is just because the conditions are just so different that the chemistry that can happen there is vastly different. Okay, so like I said, astrochemistry in the field of this, we have the study of composition and reactions of atoms, molecules, and even ions in space. And within astrochemistry, you can have three main types of scientific activities. The first is identification of species. So I have the image of the GMRT from Pune here. I think some of you at least would be quite familiar with this. So the first thing which is involved is how do we know there's chemistry happening in space? Because we have been able to identify various species using various techniques. So over here, you can see I have a range of different molecules which have been detected using various different techniques. So you have every molecular species, chemical species, will have their rotational, vibrational, or electronic transitions in different ranges. And using that, they are actually able to detect them. Okay, so over here you can see most of the detections have happened in the millimeter range and centimeter range, which is what you would have for, say, something like radio telescopes. That's the range they cover, and that's a major key technique where molecules have been detected, using which molecules have been detected. But of course, there have been other techniques as well, using which molecules have been detected. For example, IR was used for benzene, UV has been used for OH radical as well. Okay, so how do we detect these molecules from space? So these molecules, they have their transitions, but then Sandeep, can you mute yourself? Sandeep? Okay, sorry about that. We are back to the presentation. So like I was saying, the molecular species do have their different transitions. They have transitions on rotational, vibrational, electronic, but their densities can be really low. So either they are detected using emission spectroscopy, which is when these molecules will have these transitions, and you can detect these transitions or these signals from the space. Or another more common way is absorption spectroscopy. So what you would do is what all are present there, and then you have a really bright source behind it. Okay, so what you would really do is, because you can understand the space is a 3D space, okay, so with different radial distances, things will move at different radial speeds as well. Okay, so what you then have is you have something like your source, and then you have this really bright object. So when this bright object is behind your source, this bright object means it has a really large spectrum. So it will give out this radiation, this visible and all over the X-ray, all the radiations. It will go through your source, and some of it will be absorbed and some of it will not be absorbed. The ones which are absorbed will be corresponding to the species which are there in the source that you're interested in. Okay, and that is how you can also detect some species. So you can have both absorption and emission spectroscopy to detect various molecules. So using these techniques, they have identified more than 204 individual molecular species. And I say this roughly because the list is constantly increasing with the amount of new telescopes which are coming up, and new telescopes which are soon to come up as well. And within these 204 species, you basically have 16 different elements. So elements as in hydrogen, carbon, and so on. Okay, we'll come back to this this figure real soon, so I'm not going to go over this just now. So once you know what are the species you have in your space, the next step in another part of astrochemistry is construction and application of chemical models. Okay, because the space, the time scales, the distance scales are vastly different. They are really extremely high. Okay, so it is not possible for us to see how, for example, when we study a reaction in a chemistry lab, what we do is we start a reaction, or maybe within 5 to 30 minutes, we have our product. At max, it can last over days. But in space, these reactions can last over millions of years. So it's not possible for us to actually go and see this chemistry happening in real time. So what we instead do is we use chemical models, which basically involve, and some of the databases are KIDA database and the NIST database. So what you would then input is you would input all the different species you have. You would input how they can be formed, how they can be destructed, okay, and what their initial abundances was. the initial abundance in the chemical models generally always is about hydrogen. Okay, you base everything else based on hydrogen, and that's how you start your chemical models. And then based on these chemistry, based on what the reaction can happen, how fast they can happen, what temperatures they happen at, you basically can obtain the abundance of different species as a function of time. Okay. So in the previous part, I told you that you need all these reactions. So how do you get these reaction details? So we use different experimental and theoretical techniques. Okay, so you don't just have experiments like I'm going to talk about later in my talk. You have experiments you can use to calculate different molecules, the different ions, different reactions, and you also use theory. So what you do is the theory has multiple parts as well, because you can use theory not just to calculate the reaction rates, you can also need those theory efforts to see what molecules can be present, because not all molecules have been studied. So many times what happens is you have a molecule, you use the quantum chemical calculations to actually get what the spectrum would be. And that then can be used to identification of a species. Okay, so I'm talking about these three different parts, but at the end of the day, they are all very well connected. Okay, you use your experiments and theory, you then input them into your databases, which are then used for identification of species, for even chemical modeling. And based on chemical modeling, what you can also do is what are the different possible products, and then you need those experiments to confirm that. Okay, so all these three things really go hand in hand. Okay. So coming back to that really cool picture, at least I think it's a really cool picture. So you have a large or diverse range of environments within the space, okay? So you have, when you're talking about chemistry, we are really concerned with these four key parts. So what you would have is you would have dense clouds. So the key reason why chemistry within space was not thought of for a long time was because we always thought of space as vacuum. We thought of it as being empty. Maybe there's some stars, there's some hydrogen, there's some helium, but that's about it. They are really far apart and all those things. But what ends up happening, and that is actually true, a large part of the universe is vast empty space and really low densities. But sometimes what can happen is a few molecules can start to come together. And they end up forming these dense clouds. I say dense clouds, but that is totally in the context of space, how dense they are, okay? So you would have these dense clouds, they come together, then slowly and steadily, they can actually even form these protostellar environments where the star is starting to form, essentially. And then these material, because of the gravity, they will start revolving, you would have outflows, and then you would have a protoplanetary disk where now the planets are starting to form. And finally, the final thing would be a planetary system like our solar system, where we have the sun and different planets. Okay? And through all these environments, you have various environments in terms of temperature, you have very different density of molecules as well, and you have an interplay between three key species, that is the dust grain, the ice, and gas. Okay? Let's talk about dense clouds. So dense clouds are these molecular clouds where the molecules have come together in a slightly denser environment. Okay, and within these environments, you would also have some dust grains, which are basically silicate. You can also have carbon-rich dust grains as well. And the formation of that is not known quite well just yet. And you would also have ice chemistry. Because the pressures in space are so low, you would not really have liquid phase mostly. So what you would end up having is you would have these ices which would sublime directly off into gas phase. So depending on the temperature conditions, you would have either ice, you would have or gas, okay? And now within this dense clouds, this is just one example of a cloud, okay? But there will be other stars around it. So you would have this environment of different UV photons, different cosmic rays coming in. So what can then happen is these rays can penetrate into these dense clouds, okay? And within this outer region, what they end up then doing is they can ionize your atoms and they can break apart your molecules. Okay, this changes as you go deeper inside the cloud, but in the outer regions, what you would really have is high ionization rates and high dissociated molecules. And within these clouds, there have been more than 200 species detected, and this even includes really complex chemical compounds like fullerenes and benzonitrile, which was the first aromatic compound to be detected in interstellar space. Okay, and like I was saying in the very beginning, astrochemistry helps chemistry on Earth in terms that some of the long carbon chain molecules, and this is like 11 carbon chain long molecules, okay? These were first detected in space in these dense clouds, and then they were thought, oh, is it possible to actually have them, to form them, and then they were formed on Earth. And that is really because of what is the availability in space. Since there was since in environments where there's high carbon presence but low hydrogen, then what you would end up having is you would have this really long chains compared to the terrestrial environments where you have a large amount of hydrogen and water, and that is why mostly everything is hydrogenated. Okay? And within this environment, you also have ice formation and you also have heavy deuterium fractionation. So compared to what we have on Earth, the hydrogen to deuterium ratio is very high on Earth, but in these dense clouds, what you actually have is a higher deuterium fraction. Okay. So next, we move on to the protostellar environments. So what ends up happening in these environments? You also have radicals. Okay, and in these environments, the temperatures actually increase a little bit. In the dense clouds, you would have really low temperatures in the inner regions. The outer regions would have very slightly higher because of the cosmic ray. But in the protostellar, you actually start to have slightly higher temperatures, and the radicals and other gas species can actually now move a little bit freely on your ice surfaces. Okay, they're not as stuck. Because of the low temperature, there's low kinetic energy. So the molecules now in the higher temperature regions are not as stuck, so they can actually move around a little bit, and they can then recombine to form even complex molecules. Okay. Also, some of the UV photons and X-rays can also trigger some further chemistry in these environments, and that are also studied by many groups. Also, the dust temperatures in these regions, the protostellar regions, they actually become high enough that the ices can then sublimate, okay, and then go into the gas phase. And then this gas phase chemistry is also enriched, okay? Then the protoplanetary disks. So these are the disks which have the initial chemical abundances for the planet formations. You actually have these small pebbles, the dust grains start to coagulate a little bit more, and you start forming these planetesimals, okay? So you have huge range of densities and temperature in these regions, and actually this is the most rich chemical environment in terms of the chemistry that you can have. You can have the most chemistry in these regions because the densities are high enough, because the molecules have actually come together a lot more by now, and you have a range of temperatures. You have really high temperatures like 1000 plus Kelvin in a disk and less than 10 Kelvin. Now it's the opposite way compared to the dense clouds, okay? Because now you're starting to form a star. So your inner regions actually are higher temperature, and there is still chemistry which takes place actually in these environments. There are groups, and even in my department as well, there are people who actually study chemistry at 1000 plus Kelvin temperatures. Whereas in the outer regions, you still have really low temperatures, less than 10 Kelvin. And also the densities in these regions can vary quite a bit. So in the inner mid plane, so now you have to think of 3D because the disks are 3D, of course. So in the inner middle plane, you would have densities of 10 power 13 molecules per centimeter cube. And whereas as you start to move around the outer layers, the density reduces to 10,000 molecules per centimeter cube. And within this protoplanetary disk, there's a very interesting thing which comes into picture. So now you start to form these snow lines, okay? And these snow lines are formed because of this range of temperature, okay? You have, like I said, like we talked about, you have temperature of 10 Kelvin all the way up to 1000 Kelvin. So there's a gradient of temperature. Okay, and depending on this gradient of temperature, since different species can freeze out at different temperature. Okay, for example, the CO, it can only freeze until 25 Kelvin, whereas water can freeze up to 150 Kelvin. So what you would then have is all your CO would be trapped in regions which are up to 25 Kelvin. Then they will start to dissolve off as the temperature increases. And then until 150 Kelvin, you would still have most of your water in the ice phase. And the moment you go higher than 150 Kelvin, your water also starts to come off. So there's a huge gradient, and the amount of ice chemistry and the ice versus gas chemistry becomes really interesting. And this is also interesting because how much the different photons, the far UV photons, the X-ray photons can penetrate into. Okay, so there's a huge variety of chemistry which can happen, and the type of chemistry, the type of molecules involved, it changes as you're moving inside the disk. Okay. The last step, of course, is planetary systems. So astrochemistry doesn't just end with the disks, it carries on in planetary systems because you have planetary atmospheres. One of the most interesting ones amongst these is Titan, which is a moon from it's a moon of Saturn, and it has really interesting chemistry. It has a methane environment as well. It has cyanides in the environment. So there's a lot of chemistry which happens there. And then we are not limited. We also have exoplanets. We can have different exoplanets based on the type of planets they are, like super Earths, which have environments very similar to Earth. They have their lava and everything. They have a core and they have lava and everything. Then you can also have mini Neptunes, which have environments, atmosphere, which are more hydrogen and helium based, like our Neptune planet here. And then you have Jovian planets, which are more gas giants, like Saturn and Jupiter. Okay, and within these exoplanets, there have been different chemical species already detected, which is CO, water, and there's also hints of methane, ammonia, and HCN. So exoplanets are the planets which are outside our solar system, outside the Milky Way galaxy. Okay, since there are different galaxies already there, so outside our galaxy, whichever planets have been detected, and this is a very interesting field. It was given the Nobel Prize, I think, 2 years back to exoplanetary research. But yes, so exoplanets are those in planets, and they are very difficult to study, of course, because given their distance, they are really far apart. But there is a lot of interesting chemistry and astronomy happening in that field as well. Okay, no need to call me ma'am, I'm still a student. Okay. So till now, we have seen the different environments, and we've seen what are the conditions within them and what kind of chemistry can happen within these environments. Okay. There's also a very interesting field which I won't go too much into, but I want to just highlight a little bit because I think it's very interesting, and that is the interaction between dust, ice, and gas. Okay. So if you look at this part, in the early ice formation, what you would have is a silicated dust grain surface, and then you would have these early ice formations which would have mainly water, CO2, and ammonia, maybe sometimes, and carbon monoxide as well, some carbon monoxide as well. So these are the really low temperatures. As you start going higher temperature a little bit, you would have also a freeze out of you once you have started these small molecules, and you can have some chemistry here. You can form something like carbon monoxide, methanol as well, and you would also have a carbon monoxide freeze out. Okay, and then if you have a UV process, if you have UV photons hitting these ices on the dust grains, you can then form even bigger molecules like glycoldehyde and other molecules. Okay, and then they can also dissolve off. I will talk a bit more about this. And the moment you start going to slightly higher temperature, the amount of chemistry which can happen given these higher temperatures actually increases quite a bit, and you start to form really big molecules, not really big, but in terms of like interstellar chemistry, big molecules. And then in the hot cores, the protostellar cores that we talked about, when you have temperatures which are higher than 100 Kelvin, you actually have all these species coming out. because now your dust is too hot that all these species cannot remain frozen out, and they actually start to go in the gas phase, and you have really rich gas phase chemistry then. Okay, and within the ice phase chemistry, you have different people studying different things. You have to study the ice composition, you have different ice chemical evolution, because different types of energies, it can have UV photons, it can have cosmic rays hitting it, it can also have electron chemistry going in. And within the ices as well, there's a large research field which explores the mobility within these ices, because when these molecules are stuck on the ices, they aren't just completely stuck always. They can sometimes move around, like we talked about in case of the radicals. So there's a field which studies this. And then as soon as these molecules start to come out, you also have this ice and gas interplay. Okay. So I will very briefly now go into a little of ice phase chemistry. So within ice phase chemistry, these are generally, we are talking about temperatures which are really low, normally less than 150 Kelvin, because 150 was where the water was frozen out. But a lot of these chemistry is generally like really low temperatures, like 5 to 10 Kelvin temperatures. Okay. So how do reactions take place in these environments in the ice phase conditions? You have two major mechanisms. You have an LE radial mechanism. So if you see this figure over here, so what you would have is the surface actually sometimes can help catalyze your reactions. Okay, so you can have a hot atom or a molecule which comes from the gas phase on the surface, and then it has enough energy that it can actually move around, move a little bit, and meet the other species which was frozen out, form a new product, and then go out into the gas phase. Or you can have a Langmuir-Hinshelwood model where both the species are already on the surface, and if they have enough energy that they can move around a little bit, they can actually come close to each other, and then they can react. And with the excess energy, which is because only the reactions which can happen on these things are exothermic reactions. Okay, exothermic, I think all of you should know, but it's just the energies which are energy releasing reactions. Okay. And with this excess energy, they can actually go into the gas phase. So in both the cases, the formed product will always dissolve off the surface and go into the gas phase chemistry. Okay. There's a large field which I'm not touching here in ice phase, and that is based on the UV photon processing. Okay. There are a lot of UV photons which hit these ice surfaces, and then you can have different reactions happening as well. Okay, and if you're interested, I can talk a bit more about that as well at the end of the talk. But now I will move on to the gas phase chemistry, which is what I primarily do. And like we discussed, the astrophysical environments and the planetary atmospheres can have a large range of physical conditions. And to really predict the different molecules and how much they are present in these conditions, you need to have the rate constants over the wide range of temperatures. Okay, you need to have which reactions can occur at which speed. Okay, you can have two main type of gas phase reactions, which I will at least discuss here. That is ion molecule reactions, in which one species is an ion, one is a neutral species, and they can come together and they have rates something like 10 power minus 9 molecules per centimeter cube per second can react. And you can also have neutral-neutral reaction, in which both the species are uncharged species, and they typically can have rates of 10 power minus 11 to 10 power minus 9 molecules per centimeter cube second. Okay. So let's discuss, in the case of ion molecules reaction, what you have an advantage of is, since ions have this electrostatic force, so they can actually attract the other molecules. They can create dipoles, and they can actually have an advantage in terms of the reaction, which is why we are seeing that their reaction rate are actually slightly higher than neutral-neutral reaction. So how do these neutral-neutral reactions really take place? Yeah. So when you're thinking about chemistry in space, like I said, for a long time, we always thought there could not be any chemistry. And why was that the case? That was mainly thought of because of Arrhenius law. So here is the Arrhenius law, which I hope many of you have seen. And what it said was, Arrhenius law says that the rate of a reaction is directly dependent on the temperature. That means higher the rate, Higher the temperature, higher the rate of the reaction. Okay, and this is typical for a reaction which has a potential surface like this. That means a reaction goes into products, it's exothermic, but generally it will go through this barrier, which is the transition state or the activation energy. And in these cases, that's exactly what you would have. You would have the rate directly dependent on the temperature. That means higher the temperature, higher the rate. So, at really low temperatures in the space, it was thought under this law that the reactions will be too slow to proceed. You would have really slow reactions, and that would not be enough to explain why all this chemistry was happening. However, we now know that the reactions, the neutral-neutral reactions as well, can actually show non-Arrhenius behavior. That means they can either become really fast as the temperature proceeds, and that is mainly due to this changed potential surface. So what you can instead have, you don't have a barrier, but you have these molecules, two reactants coming close and actually becoming stable. That means they give an intermediate and then they form the product. So you would not have any barrier per se. You would have these molecules coming together, either forming an intermediate or forming a complex, which even though it has a transition state, has a barrier, it is submerged barrier. That means the energy level of this barrier is actually less than your reactant energy. So your reactants essentially have enough energy to cross over and form a product. And that is why you can sometimes see reactions which have a completely negative temperature dependence. That means the lower you go in temperature, the reactions become really fast, or they can have this U shape where it follows the Arrhenius law at higher temperatures, but there is a threshold point below which it starts to show positive temperature dependence. Okay? Since this is all very new, there's very little experiments and data available for low temperatures. Okay, and it is very challenging, both in terms of experiments, because you have to go to this really extremely low temperatures, which is 10 Kelvin, and that's what we're talking about. So it's very challenging for experiments and even for theory, because now you're getting into the range where tunneling becomes a lot more important and a lot more quantum chemical features come into the picture. Okay, I will get back to your question, Yashwardhan, at the end, maybe. So let's discuss how I am doing my experiments here, or how we are doing experiments in my group. So we are using this technique called CRESU, which basically stands for reaction kinetics in uniform supersonic flow. So this is a wall-less cooling technique, and it's a major advantage. So what you have here is you have this Laval nozzle. Okay, it's this convergent divergent nozzle. And this design is actually based on the rocket engines. The rocket engines use this design to create really hypersonic velocities. But in our case, we don't need hypersonic, we just need supersonic and we are happy. So what we then have is a wall-less cooling, which can help us generate uniform supersonic flows, which can last for 10 to 70 centimeters, and we can go down to 10 Kelvin temperatures. And this is the density of molecules you would have here. So you can see in this image over here, given by my colleague Ludovic, and you can see this Laval nozzle here, and you have this flow, which has been shown here because there's electron beam excitation. So you can really see the flow. All this is actually molecules which are flowing through here. Okay. And we also measure this using impact pressure measurements. Maybe that's not interesting for you, but that's another physical or a fluid mechanics part which comes into these measurements. Okay. So like I said, I will describe a little bit more about the Laval nozzle in the coming slides. Okay. So like I said, so using this technique, what we have now done is we have the low temperatures that we wanted. We have the temperatures that we really want. We can go down to 10 Kelvin now. So the next step that we do is we are using this technique called pulsed laser photolysis and laser-induced fluorescence. And for my experiments, I've been talking about the CN radical concentration. Okay. So what we are doing is we are generating, so when I'm talking about radicals, that is a neutral species, okay? And that is why these reactions actually don't have barriers and why they have such potential surfaces. So what you then have is you can photolyze the precursor like an iodine CN or a bromine CN to generate CN radicals. These are then excited in the electronic state, and when they relax back, they actually fluoresce, and you can measure this, okay? This is a spectrum which was obtained for CN radicals, and based on these different intensity lines, you can actually tell how much the relative concentration of CN was. Okay, so let's quickly go over how this experiment works. We have, like I said, this convergent divergent nozzle. So what you then have is you have this high pressure region behind it, and you have a really low pressure region here. Okay, so what then happens is in this region, your molecules are diffusing around and you have zero velocity, essentially zero velocity of the molecules. So based on conservation of energy, if these molecules actually go to these low pressure regions, they really have supersonic speeds. So since we have increased the kinetic energy of the gas molecules, the temperature within this flow reduces quite a bit. And that is how we can go to really low temperatures, okay? And for this, we need really low pressures, which we obtain using these really large pumps, and they are really large. They are 20 to 100 liters per minute flow. And here are some of the pumps that we have in our lab. So what you then do is you have your reactant, you have your precursor, and you put it into the high pressure region. It goes out, it creates supersonic flow. Then you would start a laser, the excimer laser, to create your radical from your precursor. And once you have your radical, your reaction has started. Okay, your reaction will not start till you fire this laser, because that is what is forming this radical. So you have this radical, and then this radical will start to relax. You fire this dye laser and they will start to relax. So we start measuring the CN concentration with this photomultiplier cube. We measure it over time. We can see the CN concentration is changing, and we can measure this. However, we are studying bimolecular reactions, and for that we need the concentration of not just our reactant, but also the CN radical, and we can't really do this, okay? So what we instead use is pseudo first order kinetics, and I was planning on going into it, but I think we are more physics people, so I will only go into it if in the end somebody has a question, okay? So you can use pseudo first order kinetics, and what you essentially do here is you can fix one concentration. You can have one reactant in excess, and which would be our reactant, and then you can measure this at different temperatures, okay? So we did this experiment for methanol with CN radical, and what we saw was as we go down in temperature, we actually saw the reaction rate increasing, okay? And that means it actually remains fast over low temperatures, okay? I also did some computational study as well, just to highlight how the computations and quantum chemical calculations and experiments many times go hand in hand. And then I've also done this experiment for aromatic species like benzene and toluene. And these are really interesting because of the recent detection of many aromatic species in the space, okay? And it was similar in this case. We don't have a negative dependence. What we instead have is we don't go low. We still have this constant uniform reaction rate, even down to 15 Kelvin, okay? Both for CN, both for benzene and for toluene as well, okay? The next step that we are doing now is our reactions can actually give different products, okay? And the interesting thing and why experiments are extremely important is because these products can actually change how much they are formed depending on the temperature. For example, if you had A and B products, these two products can be forming in the same ratio at room temperature. However, if you go down in temperature, A can actually be forming more than B. Okay, and that is why over in my lab, we are developing this new technique which combines the CRESU flows, the low temperature flows, with chirp pulse microspectroscopy. And that is how we can actually see different products. The advantage of microspectroscopy is since every species will have different rotational lines, we can actually measure this. So this has been done for the reaction between CN and ethane at 10 Kelvin. And you can see that over time, after the laser was firing, the product is increasing. And we can then see this product rising. And this can be done, this has been done for HCN, but you can essentially do this for all the different products. This was a one product reaction. But you can apply the same thing to reactions which have multiple products and then measure those different products at different temperature. This one has been done in 10 Kelvin. A few behind the scenes for all of you to kind of see how the experiments really go on. We have cranes to pick up our lasers. We have the excitement when we see the first signals. We have this really large pumps, extra pump as well, and everything else, and also using cranes. Okay, so even though we are doing astrochemistry, it involves a lot of other things, which I feel is the excitement with laboratory experiments. So just to summarize, there's a very famous quote by Rabindranath Tagore which says, "You can't cross the sea merely by standing and staring at the water." And that is exactly what astrochemistry is about. It's a vibrant field, and there's so many unsolved puzzles and mysteries still left to be solved, and that is why it's really exciting. And then I would just like to acknowledge the Astronomy Club for inviting me to give a talk, and my team members and the collaborators and the funding sources. Thank you.
Thank you for this wonderful talk. It was
Thanks,
really, we learned a lot of things. So now the floor is open for questions. You can go ahead and ask the questions.
Ma'am, can you answer my question in the chat?
Yes. Yeah. Hi, Yashvardhan. You said the intermediate won't be, no. So intermediate won't be more stable than the products. In most cases, what you would really have is you would have this initial attractions between the different dipoles. Let me just go back. What you would really have is you would, because your products are going to be higher energy, and what you then have is these different species are still moving around and they come together and they start to develop this bond, these van der Waal interactions for the most part. And that's why they go down in energy, but they're still not stable, completely stable, okay? They still then go to products, and that's what the product energy is actually going to be lower. Or maybe you were talking about this, that the intermediate is lower. Okay, so even though they are lower energy, it's not on a potential surface, it's not a minima. Okay, and since it is not a minima, it cannot be stable there for a long time. Even though it has lesser energy, it won't stay there for a long time. Okay, I don't know how much you are aware of the potential surfaces, and that's probably why, I don't know, it's a little difficult. Is it clear, Yashvardhan, or should I try explaining?
Yes, ma'am. We know for potential surfaces.
Yeah, so what you actually have, even though the intermediates, they are not the minimas, essentially, okay? So you would still want to go, and the energy will still transfer, the electron clouds will still change a bit to finally form our products. Okay, so these are, even though they are intermediates, they are stable in energy, they are still just interacting with van der Waals interactions. Okay, so they will then separate out.
Okay, ma'am. Thanks.
Yeah, worries. Hi, Yuvraj. What is LHC? I see a question from you that using LHC to create temperatures of 1 to 2 Kelvin. Hadron colliders. It depends, because you can't, what you really need is a lot of molecules as well, okay? Because a lot of these things, they are, I'm not exactly sure about the Hadron Collider, how how much the temperature, because it depends a lot of the magnetic properties of the molecule. So you can't apply it for all the different species or the bigger molecules that you want to study. Okay, and also another thing for in case of temperature for these studies, for reaction kinetics, you want to have molecules colliding with each other. So you want to have not just these molecules at low temperature, but you want to have enough molecules at low temperature that they can then collide and actually form your reactant products in sufficient amount that you can detect them. Is that clear? Okay. Sure, I'll be happy to share these slides. I can probably send it to Devang if he's okay, and he can forward it out.
Sure.
Yeah.
We'll also we have recorded this talk, so we'll also upload it to the YouTube in a couple of days, and then share the links.
Okay. Any more questions? I think the idea for this talk, at least from what Devang told me as well, was because many of you are interested in the very beginning field as well. So I'm happy to share, even answer any basic questions as well, given my ability or knowledge.
I had one question.
Yeah,
Question. Yeah, so you were talking about some new observations that people are looking forward to. So what kind of observations are those, or what are the things that we expect to learn?
So there's one really exciting one, which is has been postponed a large number of times, and there's a lot of memes around as well if you follow this field, and that's the James Webb Space Telescope. So there's a lot of interesting chemistry started happening when there was a Hubble Space Telescope which was sent out, and there are a lot of cool pictures which came from that project. And that's mainly because within there are a lot of radio telescopes which are on Earth, but you're always limited by your atmosphere as well. Okay, so within our atmosphere, we have so many species, we have a lot of water vapor as well. So many of the observations are limited by that range. Okay, so there's certain ranges which we cannot probe because of that. However, with the James Webb Space Telescope, we can actually now probe those IR regions, and which can really help understand ice chemistry a lot more, because water has really broad features in the micrometer range. Okay, so when you're doing observations from Earth, even though the radio telescopes are designed to be placed on really high hills, okay, where essentially the water vapor is supposed to be less, but you are still limited. Okay, so the space telescope of the James Webb Space Telescope is the one which will go out in space, and then you would have a lot more observations. And there's also been recent projects as well, different planetary projects as well, which have given more details. And the NASA Preserve as well with the Mars will give us more details. So that should be exciting.
Yes, thank you.
Okay, Shashwat. So there are, within India, I know of at least 2 people who are mainly focused in astrochemistry. One of them is Balamurugan Sivaraman, and he's at Physical Research Laboratory in Ahmedabad. And there's also Liton Majumdar, who is in IISER Bhubaneswar, who's a new faculty there, I think, for the past 3 years. And these are the 2 people who are solely focused on astrochemistry. Of course, there are other spectroscopists and ice-phase physical chemists, essentially, who are working on problems which help tackle astrochemical problems. Okay. Anubhav, I'm looking at your question now. I don't have radical. This is radical reaction. The CN that I'm talking about is a radical. Okay. CN is not a molecule. CN is a radical, indeed. So when you're talking about neutral reactions, essentially what you really have is neutral species with a radical reaction, because those are the reactions which actually have potential surfaces like this. Okay, so we do have radical reactions. We also have radical reactions, but they are really hard to study. And they are quite less as well, because of course you would have lesser concentration of radicals, so you would have lesser number of products forming from those. I hope that answered the question. Okay, Jayashree. That's a very interesting question, Jayashree. So I did think I actually went to Professor Bala, who is at PRL, for one of my winter internships after I had taken my majors. I was still doubtful if I was supposed to go from physics or chemistry. I ended up taking chemistry, even though now I'm at a place for physics. But that's the overlap, that's the interdisciplinary nature of this field. So I did once winter internship where I basically just read papers on astrochemistry because I wanted to be sure that I really liked this field enough to be in chemistry and not change back to physics. But yeah, I think even otherwise, you are always welcome to start astrochemistry at any point. It basically goes at any other experimental project, or you can still do theory work as well. So it depends on what you want to do, but I think you can always contact people. With theory, maybe it's a little more easy because you don't have a lot. The problem with astrochemistry in our department, our IISER-Mohali, our institute, is we don't have a focused astrochemistry course. So it's always going to be slightly hard to go into it. But I'm happy to share some review articles as well. And I think in every field you always start from zero. So you're always welcome to contact some professors and start reading and then slowly learn up to that. Yeah. Any more questions?
If there are no more questions, then let us thank Divita Di once again.